Hello, this is Devika. I'm an online physics tutor. Today we are going to study the topic of electric charges and fields. This is the first chapter of 12th CBSE. I just explained all the topics in one video. I just explained only the topics so that you can get a clear idea. The next video we can see the problems related to the first lesson. Okay, so it will be a quick revision and quick study for the first lesson. Let's get started. So firstly, you have to know that what is electric charges. Okay, so we have two kind of charges. One is positive charge, another one is a negative charge. Okay, the charges are formed by they are already there in the atoms itself. Okay, so we have two different charges, positive and negative charges. How the charges are formed? Charges may formed by a friction, induction, and conduction process. Here in the syllabus, they are given if you are rubbing a one glass rod with a silk thread, it will produce as a positive charge because so the glass rod losing some charges, okay, to the silk thread. So automatically and naturally all the systems are in neutral. So silk is carrying some of the negative charges, that is electron only transfer, so that this atom is now not in neutral condition. Okay, so it is positive charge and it is negative charged. Similarly, if the plastic rod is rubbed with the animal fur also, the plastic rod gaining electron from the animal fur so that it will be a negative charge. Okay, this is how the charges are formed. Here we are only seeing about the charges in a statics condition. That means we are considering charges in a insulators only, not a conductors. If it isn't conductor, it will be run away. Okay, so the first two chapters of the 12th chapter only whole about that statics, that only the charges or just hold in a insulator only. Okay. So this is all about how the charges are formed. Initially, they all are neutral. They are rubbing or conduction or induction. Some of the charges are given to the some of the material. Okay, so that it will be a lack of some charges. If the lack of electron leads to the glass rod is positive, the gaining of electron leads to the plastic rod is negative. Okay, we already know. We have two properties of charges. The like charges are repel and unlike charges are attract. These are the main important properties we already know. These are the properties of the charges. Next, we have one of the experiments related to the gold leaf experiment like that. In the gold leaf experiment, what we do, we are carrying one conductors and at the end of the conductor, we have two gold leaves. They are attached to each other. When we give a positive charged rod near to the knob, the positives carry all around the rod. It will give the positive charge to the two whole leaves so that the charges, that leaves will be spread out in a equal uniform speed. Why? Because these are the positive charge, no? So they will repel. And also they are separated with the uniform speed. That means the charges are separated. Charges are diversifying in the conductors in a uniform way. The diversification is very uniform all around the conductor. These are the only one main of the properties of the charges. Okay. So we know about conductors and insulators. Conductors carry electricity and insulators do not carry electricity. Why? Because it offers high resistance because it doesn't have no valence electrons. But in the contrary, that conductors have valence electrons. Okay. So next topic is the properties of the electric charges. We have three properties. First is additivity of the charges. Next one is charges are conserved. And the next property is potentiation of charges. Okay, I request you students to carry book with yourself so that you give the proper revision of all the topics. Okay, and I will recall all the topics in the book itself. Okay, what is additivity means? If we have one system, we have numerous number of charges, means we just add all the charges to get a total charge of the particular system. Okay. Next charge is conserved. Conservation means the total charges are not destroyed or created. It will only transit with the system. We have two bodies. We rub the two bodies. Charges only transit. It will be not destroyed. So initially we have 9 charges between the two bodies, 4 and 5. After giving 1 electron to the system, so the system will be 5 and the system will be 4. Here also the total amount of charge will be 9 only. So initial and after rubbing process, after friction also the charge will be same. That means the total charges in isotopy system is always conserved. It only transfer, it is not destroyed or created. Okay. Next is quantization of charges. Quantization Q is equal to NE. How to find the total number of charges in a particular system? This is the formula I used. N into E. E is a charge of electron. We already know the value. 1.6 into 10 power minus 19 is the universal number, the charge of electron. N is the number of electrons depending on the system. Okay, that is called as quantization of the charges. These are the three properties of the charges. Next, we move on to the topic of Coulomb's law. What Coulomb's law gives that it derives the force. We can find the force between two charges. We already know we have two charges means either repel or attraction force already there. How to find the quantity? How to find the magnetic magnitude? So we used Coulomb's law. The force is proportional to the properties of the charges and inversely proportional to its distance itself. That's the universal Coulomb's law. It is the proportionality constant we used as K, that is called as constant, and we only take a magnitude of the force only. So I just put a modulus here. Okay, or it'll be in meters. It is a very important term. So Q1, Q2 may be positive or negative. The force will be always taken as positive. K value is 1 by 4 pi epsilon naught. The value is 9 into 10 power 9 Newton. Okay. So from that formula, we know that the unit of the K value. Okay. So the K value can be calculated from, it will be reversed like this. K is equal to F R square by Q1, Q2. That means F value, F unit is Newton, R in meter square, and the charges will be in Coulomb square. So this is the unit of K value. Okay. In one final year, one words they asked this question. Okay. So next topic is they are just like the vector form of the Coulomb's law also. So 1 by 4 pi epsilon naught. Epsilon naught is the permittivity of the free space. Okay, so this is a constant which is related with the permittivity of the free space. This formula also carries the same value. Okay, and next they are deriving the formula with vector quantities. Here also we have two position vectors. So the difference between these four also the position vector difference. So we can mention it with the direction itself by using R21 Jacob. So either the two charges experiencing some force with each other. Q1 charge experiencing some force with this, and Q2 force experiencing some force with Q1 charge. So these two charges are equal and opposite. Okay, because the direction is reversed. So F21 value is this. This R cap 21 used to denote the magnitude of the charges, and F12 is completely opposite because these two forces will be repulsive. Here they take on two positive charges. So repulsive force will be happen. The direction is opposite. So the force will be equal but opposite magnitude. Okay. So this is all about Coulomb's law. This Coulomb's law can be extended to form to find the force between multiple charges. That's the next part. What if we can carry three charges? So unless of two charges, so we have to find the force between multiple charges by using the same formula. Now we have to find the force between the Q1 charges due to the charges of Q2 and Q3. So there is two combinations are there. So we use two Coulomb's law formula to derive the condition. So in this question, we have to find the force on Q1 due to the charge Q2 and Q3. Okay, so this is the final formula by using two for Coulomb's formula because Q1 is related with Q2 and Q3 also. Here we write the position vectors. So simply adding these two forces, we can get the force on the Q1 charges. If we are having multiple charges means we just add the force to the other charges. Force equation with the other charges. Okay. Okay. So next topic is electric field. We completed the Coulomb's law. Next topic is electric field. Electric field is nothing but any charges having invisible electric field around it. So positive charge having outwards direction of the electric field and the negative charge having inward direction of the electric field. So definitely it expends a force when a test charge enters in the boundary of the negative charges. Either it will be attract or repulse. Okay. So the force can be written with the electrical formula F is equal to QA. So E formula is F by Q. Already we know F is equal to K Q1 Q2 by R square. If it is divided with the discharge value Q, it will be cancelled out. So the final answer of electrical formula due to the point charge is 1 by 4 pi epsilon naught Q by R square. Okay, so this is the electrical due to a point charge formula. This is a very, very important formula. That is 1 by 4 pi epsilon naught K Q by R square. What if we have a carry so many system of charges? So how to find the electric field due to the system of charges? We have to find the electric field at the point P. Okay, we have many charges. Every charges have an electric field around it. So we take one point near to the charges, all the charges. It is from the distance of various distance. So how to find the electric field due to all the charges? Just add all the electric field due to the individual charges, like that only. E1 plus E2 plus E3. We use the same formula. KQ1 by R1 P square, 2P square, 3P square, and so same as Coulomb. Understood? Okay. Next is physical significance. So physical significance means electric field can be produced by accelerated charges and normal charge itself. In the sun chapter, we study that electromagnetic waves. Accelerated motion of the charges produces electric field and magnetic field. Simply a charge produces electric field itself. Okay, this is a very important concept. So we will study in the coming chapters. Okay, let's move on to the next topic. Until then, we have studied Coulomb's law and electric field. Next, we move on to the electric field lines. We already knew. If we have one charges, means we have an electric field around it. So the lines used to denote the electric field is called electric field lines. Okay. For a positive charge, it will be outward direction. Negative charge, it will be inward direction. Okay. So if it will be, its strength will be vary from the distance will be increased. Okay. If it is a charges, that if it is in the place of P1, its value is higher, at intensity is higher. If it is in the place of P2, its intensity will be lower. In case, in respect of number of lines emitting from Q is same, but it will be denser around the area is P. It's just nearer to the charge Q. These are the para to explain these topics only. Okay, so electrical strength depends on the closeness of the charges only. So the direction of the charge is very much important. For positive, it is outwards. Negative, it will be inwards. We have two charges. Positive means it will be repel each other. So its direction is like that. Just study these diagrams. It will be very much important. So the positive and negative charge, it start with positive and end with negative. Okay. So we know it has some properties. It is very much important. 3-mark and 2-mark question. So the field lines are starting from positive charges. It will be end at negative charges. Okay. So for a single charge, they may start and end at negativity, infinity. Okay. So these two diagrams to represent positive single charge. Okay. So in a charge-free region, the electric field lines can be taken to be continuous curves without any breaks. We see the electric field lines, it doesn't have any breaks. Okay, it will be continuous. The force will be continuous. It is not breaking in between. Okay. And two field lines never cross each other. Okay. We see that two lines are never cross each other. If it is cross each other, mean it will form a resultant vector. It shows another direction. But here the directions are defined. So it is not intersect each other. So electric field is run from closed loops. It doesn't form any closed loops. In positive negative charge also, it start with positive and end negative. Again, it start with positive and end negative. It is not a closed loop. Okay. So in the magnetic field, it form a closed loop. Okay. So these are about electric field lines. Next topic is electric flux. What is electric flux? So number of field lines through a particular area. Okay, we have separate area. We can place a material perpendicular to the field or parallel to the field, may make in some angle. So the number of field lines to the particular area, that is called as flux, that is denoted by the term of phi. Electric field with a particular area. E dot del S. Dot product means it will be cos theta. So that angle that makes between E and del S. How to find the del S vector? So if we have some area, means the del S vector should be perpendicular to the area. Okay. So, and the electric field direction they are already given. So if you find that the angle between these two vectors, you get the flux, the number of field lines through a particular area. Okay. So it's electric flux, notice this can derive from this formula, phi is equal to E dot del S. So E formula can be derived from F by Q. Del S is area, that is meter square, force is Newton. Q is Coulomb. It will be in denominator. So this is the unit of electric flux. Okay. Next is electric dipole. What is electric dipole? Electric dipole is nothing but two equal and opposite charges separated by some of the distance. That is called as dipole. Okay. So what is the unit of dipole? Dipole moment. Dipole moment can be created in the dipole. It will be start from negative and end at positive. It's a vector quantity. So its formula is Q into 2A. That means Q is Coulomb and 2A is distance, that is meter. So coulometer, that is the unit of dipole moment. Okay, this is very much important quantity, the vector, small. Next is electric field dipole. What is the field of dipole? It has two charges, right? So we have two axes like dipole axis or equatorial axis. Suppose we have a dipole like this. So we have point along the direction of the dipole, the P. So what is the electric field due to the point due to the charge Q and minus Q? This is totally called as dipole. So this is what we have to find out. That's the important question. So how you find out? We can know the electric field to the point charge formula is Q by R square. KQ by R square. This is a simple formula to denote the point charge electric field. So we have to find the two point charge electric field due to the at the point P. Okay, so we just add E plus Q and E minus Q. Here the distance is vary because from Q to this P, the distance is here. So the total distance we take as 2A. The dipole is separated into two parts, A and A. So this total area is taken as R. So we have to find this area only. So we just take as R minus A the whole square. Here the total distance will be taken as R plus A the whole square. Okay. After cross multiplying this, we get this expression. Okay. So what if the dipole at equatorial point? Equatorial point means at the center. At the center of the dipole, we get a one point. At this point, what is the dipole? Dipole due to the electric field at a point P. So it makes some angle, right? So electric field direction here is a positive charge, so it is outward direction. Negative charge, it is inward direction. If we cut two vectors, means it form a resultant vector at this direction. Okay, so here one point also added that the dipole moment direction is negative to positive. Okay, here the electric field direction also this direction. Direction also very much important because plus Q charges is very much nearer to P. So this domination is greater so that the direction is same as the dipole direction. So that final formula is taken as positive only. But here you can see, so this is the dipole direction and this is the total electric field direction. So it is opposite. So the final answer must carry minus sign, first point. Next, same way you have to find the positive charge electric field, negative charge electric field, just add to that value. But here it makes some angle with the vector. So it is resolved into two components, E plus Q sine theta and E plus Q cos theta like that. Okay. Then it is equated triangle too. So the angle is 930 only. So okay. But here also it makes the same coordinates like E minus Q cos sine theta, E plus Q, E minus Q cos theta like that. So what will happen? These two vectors will cancel each other. Okay. So that only the cos theta component will be added up, the another component will be cancelled out. Okay, so these two components will be cancelled out, only the cos theta components like E plus Q cos theta, E minus Q cos theta will be added up. So these two values having same distance like this, distance is same. We can get this distance from the Pythagoras theorem. This term is A, this is R. So root of R square plus A square over 3 by 2, 1 by 2. Okay, so and the distance is also r plus r square plus a square, the whole square. We just take this angle is theta. This angle theta will be same. We can get the cos theta value from there. So we just add these two values, get this value. It will be represented with minus sign. That is very much important. Okay. So next we simplify this formula with the dipole moment Q into 2A. So we just write it this at a point of dipole axis and the point of equatorial plane. So these two values are very much important. The expression also important. Okay, you study all them. Next is dipoles may be polar or non-polar. Some of the materials are naturally polar, otherwise non-polar. What is polar? Polar means it will be differentiated to positive and negative, means that is polar molecule. The positive and negative charges are coincide, that is called as non-polar. Okay, we will discuss in the next chapter. Okay. So, okay, let's move on to the next topic. What if the dipole in a uniform electric field? Now we already know Dipole itself having a charges. If it is in an electric field itself, already there is an electric field. In the electric field, the charge will be there. So what will happen? There will be a force developed in these two charges. It will be equal and opposite. So it will produce as equal and opposite forces. So net force on the body is zero, but it will be rotating. Let's take an example of the car steering. Car steering will be rotated only if the opposite force is given to it. So that the torque will be produced. So it's a torque formula. The general formula of torque is F into distance. So force formula we can derive from F is equal to QE. Okay. So what's the distance? So that torque will be taken as this angle with that electric field. Okay. So it is we have taken the perpendicular distance. So this is the perpendicular distance we can take in from. This value will be taken as A, and this will let's take this angle theta is sine theta, means the opposite value you have to find out, that is x by A. So the value is 2a sine theta. Why? Because I just take the whole perpendicular distance. So that the value is 2a. So x by 2a, that is 2a sine theta. I just multiplied there. So 2qa is taken as p vector, because p is equal to q into 2a. So p cross e, cross product taken as sine theta. So torque produced due to the dipole uniform electric field formula is p cross e only. Okay. So electric field direction and the dipole moment direction is very much important to find the torque. Dipole moment direction is always from negative to positive. Okay. Yes. Next is continuous charge distribution. This is a very just known topic. And we know that value, we just know the symbols, that is sigma. Sigma means surface charge density. What is the number of charges to the particular surface area? Okay, it is depending on the geometry. Okay, and linear charge density is called as lambda. So what is the number of charges in a particular length? That is del L. And the volume charge density is taken as rho. That is called as rho. So at a particular volume, what amount of charge will be there? That is taken as rho. So del Q by del V. Okay, each have a formula and the unit is called Coulomb per meter square, Coulomb per meter, and here the Coulomb per meter square. Why? Because the charge unit is Coulomb and the surface charge density value is meter square. Okay. Yes, next is important and last topic is Gauss law. So we can derive, we can get a flux value by using a general formula called eta del S, but a special formula used to find the electric charge due at a particular closed surface. Okay, we can derive this formula from this sphere. We take a particular part here. From that part, we can derive the formula by using the general formula. We just write the E value, the electric field due to a point charge, the point charge in the sphere, and this is the del S value. What is the surface area of the sphere? That is 4 pi r square. Substitute the value, you can get q by epsilon. Okay, so this whole arrangement is at a particular boundary. So then we take this del S as 4 pi r square. So that value will be get as q by epsilon. Q is the charge enclosed by the particular surface only. So we can get the electric flux value by using this formula at a case, at a condition of a closed surface only. Okay, because multiple closed surface means we just add all these value to get the total flux. Okay, so we already have general formula. This is the added formula. Just recall that. So Gauss law have some important points and with important significance. One is it definitely have a closed surface, first point, and it includes the sum of all the charges enclosed by the surface. And next is we have a surface, inside some of the charges is there and outside some of the charges is there. I mean, we just taken the inside surface charges value only. Okay, we didn't count the outside value. And the third one is it definitely have Gaussian surface, that is called a closed surface. And the Gaussian surface should be in some symmetry so that we can use some geometrical formula. And finally, the Gauss law is some resembling with Coulomb's law. Okay, it has inverse square dependence. Okay, somehow it has some difference, but it is an inverse square dependence with that value. Yeah. So next topic is the applications of Coulomb's law. After this, the topic is over. Okay, we can quickly revise all the chapters. First application is the field due to infinitely long, straight, uniformly charged wire. Let's take a wire having a positive charges will be infinitely long. We take one of the Gaussian surfaces as cylinder shape. So in the cylinder shape, we take one point. At this point, what is the electric field? Okay. This symmetry shape have three closed surfaces. That is one. The two top surfaces, one is a curved surfaces. So electric field direction and the vector, the del S vector direction is perpendicular to the surface only. It will be same direction here only, in the curved surface only. Here the direction is opposite. The del S and electric field direction is opposite. It is 90°. So why? Because the phi formula is E dot del S. The cos 90 value will be 0. So flux due to the upper part and the lower part will be 0. Only the curved part only have the flux value. So we just direct the flux formula E dot del S. Del S is the curved surface of the cylinder formula. We just equate with the Gauss law because it's a closed surface. We take one Gaussian surface. So Q is written as lambda L because Q is equal to Q by L is equal to lambda. We just cross multiply this. We get del L by epsilon. So L will due to an infinitely long charged wire value is lambda by 2 pi epsilon r, which is inversely proportional to its distance and directly proportional to its linear charge density. It is called a distance. Okay. Yeah. Next topic is the field due to uniformly charged infinitely plane sheet. Let's take one sheet. Its surface area is taken as sigma only. So it has, we take one Gaussian surface as a rectangle shape. So we have both sides the electric field values there. The DLS value is same, it is same direction. So we take two surface area, 2 into E into del S. We take area as del S as E only. It is related with epsilon, the Gauss law, that is Q by epsilon. Q value will be taken here is sigma A. Why? Because it is a surface charge density. It's a plane sheet. Okay. We simplify this, we get sigma is equal to E is equal to sigma by 2 epsilon. So the electric field due to a plane sheet value only depends on surface charge density. It is not on the area. Okay, sorry, the distance, because it's a very important one. All the three these applications only, it is not depend on the distance between the point. Like we take one point here, right? At this point, what is the electric field? But the distance is not taken here. It will be cancelled. The area will be cancelled. So next is spherical shell. Electric field due to spherical shell. This shape is carrying a volume. So we have 3 points. The electric field due to the shell are outside the point, inside the point, and on the point. We take 3 conclusions. First, we take what is the electric field due to outside the shell. This is the radius of the shell, and this is the point where we have to find the electric field. The distance is r. So we just taken as E dot del S formula. Del S formula here is 4 pi r square, surface area of the sphere. Gaussian surface here is sphere only. So we just cancel out the value. We got the E values Q by 4 pi epsilon r square. If it is on the surface itself, means that R value is replaced with capital R. This R value is replaced with capital R only because it is on the surface. Okay. What if it is inside the surface? We take in one Gaussian surface inside the surface, inside the sphere, we take radius is R only. So what is the electric field inside the shell? It had no charges, right? So the charges are uniformly distributed all over the surfaces. This is sphere. So sphere means it's a sphere shell. So it is a hollow part inside. There is no charge inside it. So if it is no charges, it cannot be related with the Gauss law Q by epsilon. The total value will be 0 only. So the electric field inside the shell is 0. Okay. So these are the 3 important applications. So in this video, we can quickly summarize all the points related with Coulomb's law, electric field, and the Gauss law, and the electric flux, and what's the electric field due to dipole at axial point, negatorial point, and what's the torque value. So this is all about this video. So we can connect with you the next lesson, and we will study some of the problems in the coming videos. Okay. Thank you. Thank you for watching. Have a great time.